Okay, good morning, ladies and gentlemen, boys and girls. Welcome to AP Chemistry. You're going to need your notes, your notebook out wherever you write important information about chemistry. Periodic table will probably be helpful as well. So let's get going. We're going to be talking about 8.2 in your book, and this is going to be ionic bonding. A lot of the stuff I think you've already seen before, but that's okay. We're going to react, first off, for an example of ionic bonding, we're going to react sodium and chlorine. Right here we have sodium in its standard state, and that means at 1 degree or 1 atmosphere and 25 degrees Celsius, we know sodium is a solid. We're going to react it with some chlorine gas, also in its standard state, and we're going to form some solid sodium chloride or table salt. You might be thinking, why do we have a half for a coefficient? And that's just because we're producing 1 mole of sodium chloride for this value, so we have to balance it this way. Otherwise, we'd be producing 2 moles of sodium chloride. We have a value down here, and first off, this value is negative, so that should tell us that this is an exothermic reaction. It's going to give off heat. What it means, though, is we have delta, which means change. H is talking about heat, or enthalpy. This is letting us know that it's the standard state, and F is the formation. So we're making sodium chloride, and in making sodium chloride, it gives off lots and lots of heat, 410.9 kilojoules per mole. Now, I want to show you a quick little video of this whole process done by a chemist at Berkeley. So here's the video, and it's only about 3 minutes long or so.
We've asked Lonnie to demonstrate the formation of an ionic bond. In this case, the bond between sodium and chlorine in sodium chloride. So Lonnie's filled a beaker with elemental chlorine. That's chlorine gas, Cl2. It's a yellow gas. He'll also use solid sodium metal. Solid sodium metal is a shiny silver metal that's very soft. You can actually cut it with a knife. Sodium metal is very reactive. It will react in air and water, so it's stored under hexane. He'll pull off a small chunk and immediately store it under hexane while he prepares the rest of the experiment. Now, to get the reaction to go, he'll want to clean the sodium, make the surface very clean, and warm it slightly to help the reaction proceed. He'll do that by placing the sodium in a spatula and then warming it over a flame to clean the surface and to get the sodium warm enough to initiate the chemical reaction. Now, the reaction between sodium metal and chlorine gas proceeds, but we know the ionization energy of sodium is greater than the energy released, the electron affinity, when chlorine accepts electrons. So the reaction goes because the positive ions formed on sodium and the negative ions formed on chlorine are drawn together, a Coulombic interaction, to form an ionic bond. The formation of that ionic bond, plus and minus charges attracted together, releases energy, and that's the driving force for this chemical reaction. And you can see that it's exothermic. Energy's being released. Bright red glow, typical of emissions from sodium. Now, the reaction between sodium and chlorine, of course, forms sodium chloride. We typically know that as table salt. And Lonnie's prepared some in advance. He has white table salt, purified, that he can show us. There it is, purified in advance from Lonnie Laboratories. And Lonnie tells me the salt that he makes in Lonnie Laboratories is far superior to any salt that you can buy in the store. So what does he have to do now? Lonnie's going to demonstrate, clearly hasn't had his breakfast this morning, that Lonnie Lab salt far superior to any salt you could buy in the store. Thank you, Lonnie, for that demonstration that sodium chloride, an important spice and food flavoring. And when you make it yourself, the satisfaction is so much more complete.
Okay, so there we have it. We have a reaction involving. So there we have it. We have a reaction involving sodium and chlorine, giving off all kinds of energy. And so let's talk about what's going on at the atomic level here between sodium and chlorine. So what happens at the atomic level? So we know this already. We know that sodium is going to form a sodium 1+ ion. We know it's going to lose 1 electron. We know chlorine is going to form a 1- electron. We know it's going to gain an electron. And that can just be seen on the periodic table. Now, in our last chapter in the test we just took yesterday, we know that sodium has a lower ionization energy than chlorine does, meaning it's gonna readily lose an electron. And we know that chlorine has a lot higher electron affinity, so it's going to gain an electron. So really, this is what happens when this whole process occurs. What we're showing here is the crystalline structure of sodium chloride, and you see that for some repeating subunits, we have this positively charged sodium, negatively charged chlorine. And if we look kind of like maybe the sodium right here, this guy is going to be surrounded by, for every sodium, is going to be surrounded by 1, 2, 3, 4, plus 1 on top and 1 on the bottom, 6 chlorines. And the same thing goes for chlorine. Every chlorine, like this chlorine over here, 1, 2, 3, 4, there'd be 1 on the outside and 1 on the inside. So that's the crystalline structure of sodium chloride, those positive and negatives attracting to each other. Now, talk about the energetics of the ionic bond formation. Now, as you guys just saw in that video and you saw in that the reaction, is the sodium plus chlorine gas is very exothermic. That's in the forward direction. Now, we're going to talk a little bit about if we take a ionic compound, we can separate this guy out by putting in energy, and so this is called lattice energy, and this is definitely a definition that you need to have down. It's kind of what we're going to be talking about for the next few minutes. The lattice energy is the energy required to completely separate a mole of solid ionic compound into its gaseous ions. So if we were going to take sodium chloride, and I'll go to the next slide here. Oh, there's a table of lattice energy, so let me come back to that real quickly. If we were going to take sodium chloride right here, NaCl, and we wanted to turn around and separate it back out into respective sodium ions. Oops, sorry about that. Go back to that. Respective sodium ions in the gaseous state and chloride ions in the gaseous state, we would have to put in quite a bit of energy. This is a positive value here, and we have delta H LATT. This is our lattice energy. So this is going to be a positive lattice energy. This is going to be endothermic. Okay, so let me drop back one slide here real quickly and just give you a table of some lattice energies. So you can see this table is in your book, and it's also in the back of the book in Appendix C, I believe. And you've got some different compounds, and they're different lattice energies. And then you have some different compounds over here, and they're different lattice energies too. And we're going to be able to look at a compound and determine what kind of lattice energy it has. And again, that lattice energy is just how much energy is required to separate a solid ionic compound into its respective ions in a gaseous state. So, how do you know what the magnitude of the lattice energy is? And we're going to use this formula, but we're not really going to use it though. We're going to know it. And this is your lattice energy right here. Is equal to Q1 multiplied by Q2 divided by D, which is our distance. And so let's talk about what each one of these things are. First off, K is going to be a constant, so we're not going to worry about it. Q1 and Q2 are going to be charges on the ions. So Q1 and Q2. So let's say if Q1 was potassium and Q2 was chloride, the charges would be a +1 for Q1 and a -1 for Q2. Okay? Because these are numerators in this fraction, as the charges go up, the lattice energy is going to increase because they're the numerator. When you multiply greater numbers together, the lattice energy goes up. D, right here, and right here, is going to be the distance between the atoms, or this is going to be our radius. And in our last chapter, we learned about how as you go down the periodic table, atomic radius increases because you have more electrons further away from the nucleus, increased principal quantum number, and as you go to the right across the periodic table, that's going to decrease because, well, increased nuclear charge, more protons. Okay, so what happens here is D is the distance between atoms. And as that radius goes down, lattice energy goes up because it's our denominator. Okay, so let's take a look at an example question that could be asked next here. Okay, so it says, arranged in order from smallest to largest with respect to lattice energy, NAF, CSI, and CAO. And so here's what I would do. First off, let's look at the charges. We have NA and F. Each one of these guys are going to have a 1 plus. We have CS and I. Looking at the periodic table, each one of these have a 1 plus. And then we have CAO. Each one of these guys have a 2 plus and a 2 minus. So from our previous formula, the distance is going to come into play and the charges. But the charges here are more important. So we're going to say that calcium oxide has the greatest lattice energy because it has the greatest distance and charges. And the difference between NAF and CSI, it comes down to the size. And we know that NA and F are a lot smaller than CS and I, which are further down the periodic table, way down there in either period 6 or 7. So we're going to say that CS and I has the greater distance and NAF has the smaller distance. So if I was going to line these guys up, I'd line them up so that CAO has the greatest lattice energy, and then if we look at NAF, it has a smaller distance, so it's going to have a greater lattice energy because these guys are going to be held together tighter. They're closer and smaller atoms. Let's take a look at another one, and we'll have you do this one now. We're going to confirm this really quickly. And so we have NAF right here with lattice energy of 910. We have CSI way down here with 600, so really small lattice energy because it's so big. And then over here, MgO 3795 is its lattice energy. So definitely those charges come into play. You try it now. So we're going to have the substitute teacher pause it right now and see if we can come up with who has the greatest lattice energy, and then we'll press play. Okay, so hopefully by now you figured out the greatest lattice energy, and let's see if we have the right answers. Yep, the answer is going to be CRN, and it's because it has a 3 plus charge, and the N has a 3 minus charge. It's got the greatest charge differential of all those ionic compounds. Okay, this is something that I don't think at all is new to us, and it's going to be just electron configurations of ions of representative of elements. And I don't think you need to write all of this stuff down, but it allows us to predict stable ion formation. And so if we write, let's say, the electron configuration for magnesium right here, in its neutral state, it's going to be neon using a noble gas configuration 3s2. And we know that. That's pretty straightforward. If it loses 1 electron, it becomes neon 3s1, which is, we know, is not stable. It's going to have a 2 plus charge. That's going to be stable because it's going to get to noble gas electron configuration. Doesn't mean it becomes a noble gas. It just means it gets noble gas electron configuration. Sorry about that. Let me go back real quick. Okay, and this is nothing new. We know that everybody in column 1 forms a 1 plus because they lose 1 electron. Column 2 forms a 2 plus, 2 electrons, and so on and so forth. Okay, just showing you electron configuration of ions. Once again, this is just chlorine, and chlorine is going to gain an electron. We know that because it's got a greater electron affinity, and we know it's going to form a 3s2 3p6, which is basically its argon electron configuration. We know that, no big deal. And one last quick one here, and this is all review stuff, and that's transition metal ions. And what these guys are going to do is the lattice energies compensate for the loss of up to 3 electrons, and these guys are going to lose their electrons in generally from the 4s or the s orbitals before they dip into the d. If they're more than 2, it'll definitely lose from the d orbital itself. Last but not least for today is polyatomics, and it's just a general term. We know all our polyatomics. There's a couple polyatomics, sulfate and nitrate, and these guys are going to be a covalent compound with an ion on them. We know that already. And that's it for today. There will be a homework assignment up on the board.